All right. It's inevitable. We're going to live near the coast. We're going to go play near the coast. It's going to happen. So how can we, as humans, minimize the effects that coastal hazards present? So there's a few things that we can do. First off is stabilization. And then there's two types. The first is soft stabilization. So soft stabilization is adding sand to replace sand that has been eroded from the beach. Beach nourishment, which we kind of talked about in the previous video. More than 370 miles of U.S. coastline have received some sort of beach nourishment. For example, in Miami, Florida, we'll talk more about Miami in lab, just not a good place to live. They spent $62 million over 10 years on nourishment, so just for their beaches, because their beaches are getting eroded away. Sea level rise, climate change, storms. It's a losing battle. They can try and spend all this money they want, but eventually the ocean's going to win. Ocean City, New Jersey, another example. They spent $5 million on nourishment, but they lost it all in 2.5 months due to storms. The ocean's going to win. Nature will always win. So there's soft stabilization, and there's also something called hard stabilization. This is when we actually construct different structures, engineer and build different structures to protect a shoreline from direct wave erosions. We can create different types of walls. We can utilize something called riprap, one of my favorite terms in all of geology, by the way, riprap. So, riprap, it's kind of a fun one. It's human-placed rock or other material. Sometimes it's just chunks of metal. Sometimes it's literally, sometimes it's just garbage. Sometimes it's just a bunch of stuff, a pile of stuff, most likely rocks, used to kind of armor shorelines, stream beds, so the edges of streams, bridge abutments, that's where the bridge kind of goes into the water. A lot of times they have riprap, a lot of stuff built up around those to protect against any water, wave, or ice erosion. So this looks like some sort of maybe lake or something, maybe a large river. So you put the riprap here, so any waves, won't eat away at this soil, because they'll take that energy, right? It's hard for a wave to break down a big old rock, and they usually use harder rock, not just any rock. Nice hard rocks like granites or other igneous rocks or metamorphic rocks. They're not going to use sedimentary rocks that are pretty easy to break down. And sometimes they use just big old slabs of concrete. If they demolished a building or demolished some sort of structure that had a lot of concrete, they'll just take that concrete and kind of throw it at the edges of the ocean, lakes, streams, etc., and use that as riprap. But when we're talking about other types of hard stabilization, those include seawalls, groins, breakwaters, and jetties. So seawalls run parallel to the shore. So, all right, you have a beach, and here's the water right here. A seawall runs parallel to the shore. Not perpendicular, but parallel to that. So it really helps to retard cliff erosion, slow it down, but it increases beach erosion. So it can protect the cliffs. So if there's a cliff and you have a seawall and you have a cliff behind it, the seawall helps to protect the cliff and any structures on top. But because it's there, the water's going to eat away at something, and so that actually increases beach erosion. We'll look at a picture here in just a second. So many geologists, including myself, believe that seawalls cause more problems than they solve. You're destroying the beach to save the cliff and what's on the cliff. Is that worth it? Probably not. So while seawalls are parallel to a shore, a groin is perpendicular to a shore. It's 90 degrees perpendicular to a shore. It's designed to trap a portion of sand from longshore drift, so that kind of parallel motion of sediment drifting along the shore. So these groins, which are perpendicular to the shore, are meant to catch some of that longshore drift, and it helps to protect beach in certain areas. But it also guess what? It causes erosion in other places. So all of these, while they help in one place, they tend to hurt in another place. A breakwater is not on the shore, but actually out in the water. So it's out in the water, still parallel to the shore, but it's out away from the beach, and it's designed to intercept waves, slow them down, so they don't come in and cause beach erosion or cliff erosion. Oftentimes, breakwaters are made of a bunch of riprap, a bunch of stones kind of all piled up. And then you have jetties. Jetties are kind of similar to groins in that they're perpendicular to shore, but they're usually built in pairs, perpendicular to a shore near the mouth of a stream. So near the mouth of some river coming into a lake or into the ocean, they'll build these jetties out, and they're designed to keep kind of a ship or boat channel open in a fixed location, so that mouth of the river doesn't get closed up from sediment deposition. It doesn't get moved due to sediment erosion. So let's take a look at some of these. So you have some structure, and you have a eroding beach and an eroding cliff, and you're like, you know what? A seawall will help. Well, yeah. So you build yourself a seawall. All right. So what's happening, though, is you're not allowing the wave to eat into the cliff, so it's going to erode something. So instead, it erodes down the beach. So the beach becomes narrower. So you're actually, while now you have a stable cliff, you don't have any more beach anymore. But funny thing, eventually that water will kind of just eat away underneath it, and the seawall is going to fail anyway. Short-term solution, still a long-term issue. Water's going to win. So here's an example. So this is in California, go figure. So this is constructed, it looks like kind of heavy cement kind of structure that they built on, they just kind of plastered onto the cliff itself. They also looks like they kind of put some other material in some places along along the shore here in an effort to not cause cliff erosion. But what's going to happen is this beach is going to go away. So these houses may be okay for a while, but they're not going to have any more beach to go to. Right. There's a little story if you want to read about this area and what's occurring there. So these are groins. All right, these are groins. So seawalls are built perpendicular to the shore, on the shore, away from, kind of back from the beach. Groins are perpendicular to the shore. So usually they're kind of built, there's a number of them. And then you get some longshore drift. You get this longshore drift occurring just off the beach. And what it's going to do, as that longshore drift, as that sediment in that water is drifting, it can get kind of pulled in here, pulled in here, pulled in here. So you'll get actually sediment buildup in the direction of longshore drift, but on the other side of that groin, you actually get erosion. Again, if you build up one place, you're losing it in another place, most likely. So on one side of the groin, you'll see this kind of bar of sediment coming way out, but on the other side, it begins to eat away until eventually it's going to eat through to the other side. So here's an example of that with a bunch of groins here. Can you tell which way the longshore drift is occurring? All right, so look how this sediment builds up on this side, but it's much further back. It's eroded on this side. Builds up on this side, much further back here. It's indicating that the longshore drift is kind of down and to the left, down into this location. So that sediment builds up here, but it's eroded here and here. All right, so here is an example of a breakwater. So here are some groins. So a breakwater, what you'll see again, it's a structure built not touching the shore, away from the shore. It dissipates the energy of a wave, but what you'll tend to get is where the breakwater is directly towards the beach, you do get deposition where you're not getting a lot of water movement because waves aren't coming in there, so a lot of sediment will get deposited, but just to the sides of the breakwater you'll get erosion. Again, where it builds up in one spot, it usually gets eaten away in another. So if you look at these breakwaters here, you can see directly at the beach you get a buildup. Right, directly at the beach you get a buildup, but in between the two you get some erosion. Again, build up, in between the two, erosion. Here's another example. This is a beach that I used to go to as a kid all the time in Ohio. Like breakwater, 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 in between them, how there's erosion, in between them, erosion. And here we have a groin. Here we have a groin coming out here. So you can also tell that the longshore drift is going in this direction because you get buildup on this side of the groin and you get erosion on this side. And you can see, unless they do something, nourish the beach, it's going to continue to kind of eat in that way. And then we have jetties, similar to groins, but again, they're usually in pairs at the mouth of a river. This is the direction of longshore current, so similar to a groin, it will build up on one side, but erode on the other side, all in an effort to keep this channel open. So here's a pair of jetties, giving access to whatever this body of water is here. Which direction is the longshore drift? Is it to the right or is it to the left? So look how much sediment is here. Look how much sediment is here. So in this case, the longshore drift is going to the right. It's building up here. It's eroding here. Here's a nice little graphic that really goes into all of that. Breakwaters, jetties, groins. The only thing you don't see here is seawall. When it says littoral current, that's the longshore current. But it does a good job of showing deposition and erosion with the different types of structures. All right. So this is a good a good image to kind of burn in your brain, just in case we encounter stuff like this. We will look at these sorts of things. We will look at these sort of different structures in lab using Google Earth, everyone's favorite. I know it's a good tool. But we will look at this again. So make sure you kind of understand these different structures.